And away we go.
This is our third in a series of lessons dealing with reaction stoichiometry. In our first lesson, we learned how to make mass-mass calculations. That was followed by learning how to calculate percent yield, and now we introduce the concept of a limiting reactant. Please note on this slide that you see the term reactant. Okay, reactants are starting substances in a chemical reaction. And we're going to assume that in these reactions we have more than one reactant. Well, those reactants fall into one of two categories. They can be considered limiting or excess reactants. A limiting reactant is simply best thought of as being the reactant which gets consumed first. In other words, we run out of our limiting reactant first. And as a result, we can't produce any more product, so our reaction comes to a screeching halt. Well, simply because we've run out of one reactant, we may actually have more of another reactant available. That one would be said to be present in excess. Perhaps an easier way to think of that is this is the leftover reactant. Let's take a look at a non-chemical example. Let's suppose we want to make some French toast. Our recipe for French toast calls for 3 eggs, a quarter cup of whole milk, and 6 slices of bread. Okay, keep those numbers in mind. 3 eggs, quarter cup of milk, and 6 slices of bread. Well, if you have an entire loaf of bread, a gallon of milk, and 3 eggs in your house, and we're going to make French toast, which one of those ingredients will get consumed first? And I think you can see quite clearly it's going to be the eggs. Okay? Once we've used those 3 eggs, we can't make any more French toast. And so consequently, eggs is going to be our limiting reactant in this non-chemical example. Bread and milk would be said to be present in excess. Here's another non-chemical example of the limiting reactant concept. Okay, if I have 8 car bodies, I'm in the automobile production business, and I've also got 48 tires available. Well, I think everybody knows by now that it takes 4 tires per car. So if I have 8 car bodies, I need 4 tires for each of those bodies. Then by the time I put tires on each of those cars, I'm only going to use up 32 of those tires. So I'd have 16 tires left over. Tires in this case would be my excess reactant. The important thing to know about a limiting reactant is once we have identified it in a chemical reaction, every calculation after that has to take into account the limiting reactant. And what that really means practically is that once we've identified our limiting reactant, every calculation we make after that has to begin with the limiting reactant. So the question arises, how do we know we're looking at a limiting reactant problem? Well, look at the problem we've got here. You should recognize this as a precipitation reaction, or at least a potential precipitation reaction. We're starting with potassium iodide and lead 2 nitrate. Our products are lead 2 iodide and potassium nitrate. Well, we're told in the problem that we have 30.0 grams of potassium iodide along with excess lead 2 nitrate. If we're told that one of our reactants, in this case lead 2 nitrate, is present in excess, then it's not a limiting reactant problem. Here's another example. This one simply says how many grams of sodium chloride can be produced from 75.0 grams of chlorine according to the reaction below. Okay, we know that we're starting with 75.0 grams of chlorine. We're not told anything about the amount of sodium that we have. So consequently, we make the assumption, and this is appropriate in chemistry, that sodium's available in excess. Consequently, this is not a limiting reactant problem either. Well, you should suspect a limiting reactant problem anytime we're given specific masses of more than one of the reactants. Okay? In this case, It says we're starting with 50.6 grams of magnesium hydroxide. We're going to react it with 45.0 grams of hydrogen chloride according to the reaction below. Okay? We're given specific masses here, 50.6 grams of magnesium hydroxide, 45.0 grams of hydrogen chloride. That is a certain sign that we're dealing with a limiting reactant problem. Okay, so be aware, anytime you're told the exact masses of two or more reactants, that's a limiting reactant problem. And I provide one final word of caution here, and this will be plainly evident when we take a look at our first sample problem. You can't simply look at the masses and determine which particular reactant is in fact limiting. What I'm saying here is we've got 50.6 grams of magnesium hydroxide and 45.0 grams of hydrogen chloride. Just because there's less hydrogen chloride available than magnesium hydroxide, there's no guarantee that hydrogen chloride is in fact a limiting reactant. You see, you have to take into account other factors like the molecular and formula masses of the respective reactants, as well as the mole ratios. So be careful about that. As I tell you down here in red, the only way to identify the limiting reactant with certainty is through mathematical calculation. Okay, here's our first limiting reactant sample problem. Before we go any further, make sure as always that you've got the usual materials. Something to write with, something to write on, periodic table, calculator, and handout of common oxidation numbers. This problem reads as follows. A 2.00 gram sample of ammonia is mixed with 4.00 grams of oxygen according to the reaction below. And you'll see that there is an unbalanced chemical equation there. What is the limiting reactant and how much excess reactant remains after the reaction has stopped? Well, the first thing I want to point out is notice that in the problem as stated, we are told the specific masses of two reactants. We've got 2.00 grams of ammonia and we've got 4.00 grams of oxygen. By the way, I might ask, how many significant figures each of those contains, and hopefully by now you know the answer is 3. Well, what else do I need to do? In order to solve any of these reaction stoichiometry problems, I need to balance the equation. And since I've already done that on the side here, I know I need a 4 there, a 5 here, 4 in front of nitrogen monoxide, and I'm going to have 6 waters. So I've got a balanced equation. Next thing I need is the molecular mass of ammonia. Well, nitrogen is 14 AMUs. It appears one time in the compound of ammonia. And then I need hydrogen as well, and it contributes 3 AMUs. And so the total molecular mass for ammonia is 17 AMUs. But remember, once again, we're not interested in single molecules. What we're interested in is moles. And here's how we go about solving the problem at this point. Okay, we've done nothing new up to this juncture. You've already done these things in mass calculations as well as percent yield calculations. And I know it says that we've got 2.00 grams of ammonia and 4.00 grams of oxygen, but I'm going to put a question mark over oxygen, just as if that 4.00 grams wasn't even there. And so the question I'm really asking when I do that is, if I use 2.00 grams of ammonia, how much oxygen do I need? And here's what that calculation is going to look like. We're going to start with our 2.00 grams of ammonia. As always, we're going to convert to moles. 1 mole of ammonia is 17 grams. What comes next in all of these problems? Well, it's always the mole ratio step. I've got 5 moles of oxygen for every 4 moles of ammonia. And all I'm doing here is using the coefficients from the balanced chemical equation. Okay, what that step allows me to do is make the jump, if you will, from ammonia to oxygen. Oxygen, well, one oxygen atom is 16 AMUs, but remember, oxygen's diatomic, so it's 32 grams in a mole of oxygen. And I do a little bit of calculator work and I find out 4.71 grams. Now, perhaps the most important part of this problem is for you to understand exactly what it is I've just calculated. What this says is if I use 2.00 grams, which is all the ammonia that I've got, I would need 4.71 grams of oxygen. The question to be asked, do I have 4.71 grams of oxygen? And it's obvious, I don't have that. So what I've just done is determine that if I want to use all 2.00 grams of my ammonia, I don't have enough oxygen to do that. I've only got 4.00 grams. And so what I've just done here is determine that oxygen is my limiting reactant. Interestingly, notice I actually started with more oxygen, 4.00 grams. Okay? So just because there's less ammonia, that doesn't guarantee that it's going to be the limiting reactant. There are other things that come into play, namely molecular masses and mole ratios. Well, we've identified our limiting reactant, which is the first thing that we're asked for. Then it says how much excess reactant remains after the reaction has stopped. What I'm going to do now is start with my 4.00 grams of oxygen, and I'm going to put a question mark now over the ammonia. And so here's what that problem is going to look like. I'm going to go 4.00 grams of oxygen and 1 mole of oxygen, as we used in the previous setup, 32 grams. What's our mole ratio? Well, it's going to flip. It's going to be 4 moles of ammonia for every 5 moles of oxygen. And the last step is go from moles of ammonia back to grams of ammonia by multiplying 17 grams over 1 mole of ammonia, and I get 1.70 grams of ammonia. Okay? Here's the interpretation of this calculation. If I use 4.00 grams of oxygen, which is all of the oxygen I've got, I only need 1.70 grams of ammonia. How much ammonia do I have to begin with? 2.00 grams. So how much excess do I have? Well, at this point, it's simply a matter of subtraction. 2.00 grams minus 1.70 grams, and I think you can see that's 0.30 grams. If we're going to be really thorough, put it in scientific notation. That's 3.0 times 10 to the minus 1 grams of ammonia in excess. We're out of time, so we're going to have to move directly to a practice item. You'll see the problem stated, the equation, and then the series of 3 questions below. The most important thing I would like to see you do is simply identify the limiting reactant. If you can't get any further than that, that's okay. Good luck.